or an hour. There's going to be one, again, just a little hint towards you. There's going to be one on kinematics, which is geometry of motion, and then one F equals ma type problem, right? If you've done your homework through today and you understand how to do your homework, you're going to be fine, right? How do I make the exam? I literally have like 20 old dynamics books from different authors. I just open those things up and I flip through it and I find ones like that looks like a good one. I make sure I could do it first, right? And if I could do it, then I just throw it on the exam. So if you could do your homeworks, you're going to be just fine, okay? Unless you panic. Don't panic, because you start panicking, just rely on the methods that we've laid out, okay? Obviously, we spent a bunch of time on this orbit stuff. I thought that was really cool. I mean, within, one page of notes, we're able to calculate, the velocity, the relationship between velocities, mass of the object that something is in orbit about, and the height that they are, right? I thought that's pretty cool. Right? And then clearly we figured this out because we do have satellites up there that we're talking to, right? And just to push to, yes, the world is actually round, right? It is spherical, and we have satellites out there, and we have ways of proving that, right? Okay, so, another comment I want to make about that. Oh, one thing to mention, right? When we were talking about geosynchronous orbits, right? We determined that geosynchronous orbits were way out there. I don't know if I ever calculated that. Yeah, 35,000 kilometers away or 22,000 miles away. So that takes a while, even for light and radio waves, to go that far, right? So when you're surfing the internet, right, and you're talking to somebody over in Europe, right? Or if you're talking to your mom over there in Australia, right? You would think like, oh, maybe it's bouncing off a satellite. It's not bouncing off a satellite. That takes too long. It would take too long to go 22,000 miles for those radio waves to go all 22,000 miles and then bounce back, because that's a 44,000. I did that in my math in my head. 44,000 mile round trip for that, and even for the speed of light and radio waves, that's too long. And so that's why we have all those underground cables that are going through or underwater cables that are going across the ocean and stuff like that, which I thought was pretty interesting. Right? It's not going through those satellites. Those satellites would take too long. It's faster just to go through landlines, basically. Okay, so the next step, right? So we're all still in kinetics, right? Kinetics. We just did F equals ma, right? Now, and I said this before, so this is what the next exam is going to be on. So next week you're going to have, I think, just like 3 problems on your homework so you can prepare for your exam. Okay, but so the next 2 items that we're going to cover are work energy. This is my favorite methodology, right? This is most straightforward to me. So we're going to do work energy, and then we're going to do impulse momentum is to handle collisions. Okay, so under work energy, let's talk about when you would use this. Okay, and so that's part of the deal is when you get in here is figuring out like what methodology do I want to use. When you would use work energy problems it doesn't work all the time, it only works some of the times, is when you have multiple states. Okay. What do I mean by multiple states? So it's like it's going from, here's this object up here at state 1. What is the mass, or what is the velocity down here at state 2? So it's like, here it is up there. What's happening over here at a different state, right? Or I'm holding on to a spring and I release it. You tell me, it's max velocity down at the bottom. Talking about 2 different states, going from one state to another. Okay. Usually there's different heights, right? Different spring compressions, right? Multiple velocities. I'm just getting out of hand here. Multiple velocities, right? And then typically no mention of forces or accelerations. Right? So it's just like what's happening here is going from one state to another state. There's no mention of forces or accelerations. Sometimes work energy gets mixed in with F equals ma and you have to use both methods. But typically you're not after a force, you're not after acceleration. Right? You're usually after a velocity or a different height or compression or something like that. Okay. So we're going to start with this derivation right? And when you do this derivation, you actually do it via normal tangent coordinates. And so if we've got a particle over here, I've done a lot of the derivation for you, but we'll step through it. And so our coordinate system, we've got ET going this way. And then that's EN rather. EN's pointed at the back at the center of curvature. ET is tangent to the path. Right, and if it's going from one state to the other state, we can define what dr is. Dr is the change in the r position. Is going to be equal to ds in the ET direction. Right, the change in arc length in the ET direction. That's what our change in r vector is going to be. We're going to use that in the derivation here in a second. Okay, and so when we do this derivation, we start it with F equals ma. Just to show you that it's all based off of Newton's second law. Sum of the forces is equal to mass times acceleration, right? That is our Newton's second law. And what we're going to do is we're going to take this whole thing and we're going to dot both sides of that equation with dr, which we're allowed to do. You could, right, that's just algebraically, I can do whatever I want to an equation as long as I do it to both sides of the equation. So this would do that. It would do a dr on the first part of the equation and times dr on the second part of the equation. You're allowed to do that. Okay? So we just hit both sides with dr. So that's what this is. Okay? F dot dr is equal to mass of acceleration dot dr. Absolutely could do that. So just starting out with Newton's second law, hit it with a dr. Totally can do that. Okay? We just said this. The change in r, right, is equal to just ds in the ET direction. But this is, at this next step right here, all we're doing is expanding this, right? Normal tangent coordinates, these forces, there's going to be ft in the ET direction, and those forces right here are going to be Fn in the En direction. So both of those, I just expanded that into its vector form, right? Some of the forces vector is equal to some of the forces in the tangent in the ET, some of the forces in the En, and that's just going to be dot with ds in the ET, which I just substituted in right there, ds in the ET, which I substituted in right there. Okay, so that, everybody with me, that's totally fine. We haven't done anything too crazy here, right? The way dot products work, right? This is a projection of one vector onto another vector. If you remember back to your calculus classes or wherever you learned about dot products. You learned about dot products? Yeah, right. So it's a projection of one vector onto another vector. So if I'm trying to, these things are orthogonal. ET and EN are orthogonal. So one projected onto the other is going to be 0 because they're not projected onto each other because they're orthogonal. So ET dot EN is equal to 0. So wherever we get an ET dotted with an EN, we get 0. Whenever we get ET dotted with an EN, we get 0, right? But if we have an ET dotted with an ET, we get 1, right? A projection of one vector onto another vector that's the exact same vector is just going to be 1, okay? So basically what happens is these EN terms go away, right? And what you're left with is this. Right? We're headed somewhere, trust me. Just gonna stick with me for a little bit, right? So Ft ds is equal to mass of acceleration ds. Okay? We're gonna do another little, this is just the chain rule right here. We're gonna take this little chain rule, right? We've done this several times, right? Acceleration is just dv dt, but if I multiply by ds over ds, and I can kind of get a velocity back out of that thing. Okay? And so then we're almost there. So what happens is, so this term right here, f dot dr, just becomes ft ds, okay? And then this other, I want to box it, let's see. Just becomes ft ds, and then the mass times acceleration ds becomes mv dv. Right, I just did all the, God dang it. Come on, mister. You son of a bitch. We don't need to do it, but now it's a challenge. Okay, got it. All right. Okay, so I mean, that's it. All of the stuff in the middle is just the substitution happening as we go along. But that's ultimately what the result is, right? Some of the forces in the t direction, ds, is equal to mass times velocity, dv, okay? And so since those are just we can just turn those into integrals, knock the ds off and knock the dv off by carrying out integrals. Okay, so we're going to carry out an integral of the integral of f dot dr, right? And this is the states going from state 1 to state 2. All these things are about going from one state to another. So if I take the integral of the forces going from state 1 to state 2, right? You carry out the integral on the other side. This is going mv dv, going from v1 to v2, again from state 1 to state 2. What you get is this. Okay. What is that stuff on the side? On the right? What are those? Kinetic energy, right? Yeah, so 1/2 mv squared is what we're going to call kinetic energy. So what this statement tells us, right, we just started out with f dot dr. That's all we did, right? Started with f dot dr. Or sorry, we started out with some of the forces is mass times acceleration. We hit both sides with dot dr. We did a little fancy math as we came down there. We carried out some integrals, and what it tells us is that forces acting over distance cause a change in kinetic energy, right? And so, this is fundamental to how we do these problems, right? And just starting out with just the F equals ma. Again, the fact that people came up with this back in the day is just phenomenal, right? Like I said, my favorite methodology. Okay. And this is work, right? Forces acting over distance. Work is forces acting over distance. And then this is change in kinetic energy. Kind of a neat little finding. All right, and then just to summarize that. Cause a change in forces acting over distance cause a change in kinetic energy, or work, right? Work causes a change in kinetic energy. Work done by external forces. We'll add that to it. Work done by external forces cause a change in kinetic energy. Right? So let's kind of clearly define what kinetic energy is, right? You might be used to doing kinetic energy as KE because kinetic energy, right? So in your physics, you might be used to that. But for whatever reason, the book has gone with T. At least there is a T in kinetic energy, right? At least there is one in there. But they're going to define kinetic energy as being T. Again, I'm not sure why, right? And so T is going to be defined as equal to 1/2 mv squared. I'll clearly define what kinetic energy is. And again, we're going to call it that. Work, right? Work by external forces, right? They call it U. Again, no U in work unless you misspell it, right? Phonetically, there's a U in there. Work, right? So then that's why that one's a U, right? When in my notes, just to try to make it clearer, I usually put legs on my U. I usually I double up the legs just so, because my U's and my V's, they all start looking alike. So I'll call it out. Well, I'll just put the legs on the top of that U just to say that that's the work, right? So work done, again, usually talking about going between two states. So I would say, sometimes you go work done from 1 to 2, you put an arrow in there. Or sometimes I just go, your work done from 1 to 2. Sometimes we're going to have 3 or 4 different states. And so it's something nice to put the little subscript on it. but work's done between two states. And so usually I put the states there. That's going to be equal to the integral of F dot dr. Again, going from state 1 to state 2. Okay. So that's clearly defining that. Okay, units on these. Units. Okay, gonna be in joules. Gonna be in kilograms, meters to the second per second squared. Okay. This should be put a times in there. Right, and then in English units, we get foot-pounds. Okay, that's usually what we refer to those things to be in. I guess this here too could be a Newton meter. Right, usually it's units is a force times a distance, right? So a Newton meter, a foot-pound, right? They have work in metric units, has a unit, it's joules. Is that what our horsepower is? Or is that, I don't know. Yeah, just do foot-pounds for this, right? And keep in mind, joules, for whatever reason, about half of people, I've done an example on a homework, or on a, I've done this in an exam, and people are doing it in English units, and then I get to how much energy was in this thing, and they give it to me in joules. Joules only works for metric units, okay? Joules is a metric unit, okay? Otherwise, just put it in foot-pounds. Okay, any questions about this so far? I'm just kind of slowly going through it. So what we're going to do is, so we just define kinetic energy and work. I'm going to talk about some properties of how some of these forces work. Then we're going to introduce these things called conservative forces that are independent of paths, which will then lead us into this discussion of what potential energy is, right? And then once we define the potential energy, then we'll be ready to, we'll apply conservation of mechanical energy, which will help us solve these problems. Okay. Just so that you know where we're headed. Right. So we've just defined kinetic energy, we've defined work, and let's do this right here. So we're going to talk about this thing going from state 1 to state 2. Usually in my notes I do this. I usually clearly label right in the middle what state it is, and usually I circle it just so it's the same object. Right? It's just moving from state 1 to state 2. Okay? And this object is going to have a force P. We're going to say that surface has friction, so it's going to have a force F. I'm going to have mass times gravity acted down on it like this. I'm going to have a normal force acting up like this. Right? And that thing is going to go from state 1 to state 2. Again, I always try to make it really clear that what the two states are. It's the same object, just in two different positions. So it's going to go from state 1 over to state 2. Okay? Let's talk about what some of those forces are doing. Right, just to kind of highlight some key concepts here. Okay? So if we talk about forces doing work here, okay? Normal force. Will that normal force do any work? No. Right? The reason the normal force is coming about is because it's resisting motion in that direction. Right? That's the whole point of the normal force. It says it cannot go down through the floor. You must stay up there. Right? That's what that normal force is doing, which means that there's never going to be any motion in the direction of the normal force. Right? There can't be. Right? It's there because it's not moving. Right? And so it's not ever going to cause any work. Force does not do work. Never will. Right? It only comes about because it's resisting motion. There has to be motion in a direction in order for that to happen. How about mass times gravity? Does it do any work? Can it do work? Does it do work? Somebody? Hey, dog? Dog, you got it? Is the mass center of gravity doing anything? No. Good answer, right? It's not in this situation. Why is it not doing any work in this situation? It's not moving vertically, right? It's not going up and down. Sure, kind of indirectly it is. Mg is causing a normal force. The normal force is causing the friction, right? And that friction, so it kind of indirectly is part of that. But it isn't itself is not doing work. But it can do work, right? It can do work if there is changes in height, right? But in this particular situation, there's no change in height. It is not doing work. Mg is not doing work, but it can do work if there is a change in height. Okay, so little key concepts there. Okay. Okay, so we're talking about going from state 1 to state 2, right? So if that load P is applied, is P gonna do work? Yeah, right? P is gonna do work because it's acting over the distance, X, okay? So the work that P, so let's write down what P is doing. Okay. And sometimes you put a little substitute on this, we'll go, or a little subscript on it. U of P is equal to the integral of P dot dr. Right, these are vectors. I'll show you vectors here in a second. This just becomes P times X. P is constant, right? If you have a constant load, that integral just becomes P times the distance over which it acts. Okay? So that's just P times X up above there. Okay? So P does work, absolutely, right? Force times distance. Again, if P is constant, it's just gonna be P times the distance that it acts. Most of our problems are gonna be that. I don't think we ever actually have to carry out the integral, but I technically could give you a force that's changing with time, and then you look at it. Usually most of these problems don't do that. What about friction? Is friction gonna do work? Absolutely, right? It's a force that's acting over a distance, right? So that does work. We'll call that U of F. All right. Equals the integral of F dot dr, right, in its most general form. The one difference is between these two, right? It's going to be F times X. Okay. Do you think it's going to be a positive F times X or a negative F times X? Negative, right? It's going to be negative, and I'll write this down in a second. Why that is, right? There's a couple reasons, right? I mean, I think if you just keep track of signs, right? This is a positive P, this is a negative F, right? And so based off of that, it's acting in the negative F direction. But then also ultimately, right, we're talking about energy, right? Where this is gonna go on the left-hand side of our conservation of energy equation, right? And it's how much energy is either being put into the system or being taken out of the system, right? Is what this thing is. So P is adding energy to the system, right? It is acting in the direction of motion, right? And so it's increasing its speed, right? It's gonna be one speed, you have a P that's acting in the same direction. It's gonna be doing positive work because it's adding energy to the system. Whereas the friction force, right, is acting opposite that direction and it's pulling energy out of the system. Right? If you imagine just a block that you put up on a slant and you let go of it and it starts sliding down, right? It's going to be slowing down as it goes down because you have this friction force that's acting up that might be big enough to actually stop it, right? If you imagine the slope not being enough, you let go of it, slide a little bit, and then the friction force will resist it and it'll stop because it's pulling energy out of the system, okay? And so friction force will always do negative work, right? Because it's always resisting motion, right? It's never making you go faster. It's always pulling energy out of the system, okay? And so frictions always are negative, okay? So let's write down some of those concepts there. What did I say here? Yeah, if force acts in direction of motion, it does positive work, else negative. Right. Again, if you just keep track of signs and which direction things are going, that'll work out. But I usually do it in terms of, is that acting in the direction of motion, is it not? And that's where my positive and negatives come up, okay? And then because of that, friction always resists motion. Always do negative work. Always acting against motion, right? And it's pulling energy out of the system. Where's that energy going? In friction. Heat. Yep. It's coming out and it's getting kicked out as heat. I literally on my leg right now, on my leg, I have a perfect part circle from the rotor from my bike. Because the other day I was riding and I stopped to make an adjustment on my bike and it was on a downhill section. I leaned that rotor up against my leg and then all of a sudden I felt the burning sensation. It was because of the friction that had gotten into that. So don't do that. I recommend not doing that. Let's see if I got it. You can see a little remnant of it right here, little circle. Also note the best legs 1996 as you're going here. See that little circle right there? That's from the rotor of my bike. Yeah. I think probably the most depressive part of my leg is my calves. So you saw that. That's the one thing I gave my kids. I gave my kids my calves. And one positive thing. I gave my kids lots of things, but one positive thing I gave them was my calves. They're welcome. Okay. All right. So yeah, absolutely, it gets dissipated as heat. So when we talk about, later on we're gonna talk about conservation of energy. We're talking conservation of mechanical energy, because there is some energy in there that we're not gonna be accounting for, and that's heat and sound and things of that nature. All right, what this one does, we'll just go through this pretty quick. So this was like, what happens if our force was offset? Same idea, P going that way, but what if the P had a little angle to it? And I was just going to show you here how that dot product would work, right? So in this case, if I had that situation, I'm just going to go through this pretty quick, but if my forcing function P had P times cosine theta in the I plus sine theta in the J, right? If you did this, right, this is how you would do it, right? You would set up your P in the I and the J directions, right? And then my dr in this situation would be equal to x in the I plus 0 in the j, in the equation up above there. And so when I do p dot dr, you would have p times cosine theta in the I plus sine theta in the j times, or dotted rather, x in the I plus 0 in the j. Right? And anytime, same rule with the dot product up above there. Anytime you get an I dotted with an I, you get a 1. Every time you get an I dotted with a J, you get a 0. And when you carry that out, right, it gives you that X component. P cosine theta times X is the answer. Right, that's what that dot product is doing in there, right? Only the part of the force that's acting in the direction of motion, right? The P that's acting in the vertical direction doesn't do work, right? Because there's no motion in the vertical direction. There's only motion in that direction. And that dot product will take care of that, right? So if you're doing these things and you're, again, careful with your vectors and stuff, you can trust that dot product to do the heavy lifting and just pull out the part that's important. Okay, which is just the X direction. Or you can just apply your logic and be like, oh, well, I know the vertical, there's no motion in that direction, so it's just going to be the X component that's doing work. Okay? All right, conservative forces. All right, this idea of conservative forces. Right? So if I'm taking, so this is now I'm looking down on two blocks. Okay, so that one before we're looking at it from the side. This I'm looking down on it to look at the path. Right? If I was if I was going to move this thing from state 1 to state 2, right, and I was going to do it along this path right here, that's going to use a certain amount of energy going from state 1 to state 2. If I went from state 1 to state 2 along a different path, like this, uh-oh. They have a new thing where if you scribble on it, it'll erase it. So I thought I was scribbling, and so it erased it. All right. So which one of these would do more work? Right? If this is, I'm looking down on it from above, which one would I have to do more work on to do this? Right? The red one, right? Because it's gonna be path dependent, right? Because I'm looking down on it, if I was just moving, shoving something across the ground, if I do a straight line, that's a shorter distance, so it's gonna have less work. But if I'm squiggling back and forth as I go across, that's gonna do more work, or I have to do more work to overcome that friction, okay? So that would be what you could call path dependent. It depends on the path that you take to get from state 1 to state 2, okay? So let's define that. We're working up to this special kind of force that we're going to say is conservative, okay? Typically, forces are path dependent in terms of work being done. I'm going to put little dashes on there. If work is not path dependent, the forces doing work are considered conservative. Okay. So one type of force that would be considered path independent or being considered a conservative force would be gravity. Okay. So if I was talking about, again, paths is something to take. If I take my coffee mug right here and I lift it up to here, right, I've done work, okay? But if I lower it back down and then I go up a little bit higher, and I go a little bit down, a little bit higher, a little bit down, a little higher, that's the same amount of work that would be from going from here to here, right? And the reason for that is every time I go back down, I'm giving energy back to the system, okay? And so that's why it gets a little confusing. But right, so if I go up, I've used energy to take this coffee mug up. But when I go back down, technically this system is giving the energy back to me. Work is active. Mass times gravity, I was going up against mass times gravity, then I'm going with mass times gravity. Then I'm going up against mass times gravity, then I'm going with it. And so if I'm talking the system from going from one state to another state, and I'm tracking how much energy is, that would be path independent, because it doesn't matter if I was like, if I want to figure out the total amount of energy to go from here to here, right? I'm trying to figure out that energy. That's independent of if I go like this or if I go like this. Okay? It's kind of weird because they're obviously, me physically, personally, I had to do more work because it's like doing reps in the gym, right? I'm doing it over and over and over, but my system isn't a that's not a conservation of energy type system we're talking about. Okay? That's one type of system. So gravity, we're going to consider that. The other one would be a spring. Right? The spring would do the same thing. If I stretch a spring, I had to do work to stretch it. But when it compresses again, it gives me the energy back. And I pull it out again, it gives me energy back. And so going between two states, it doesn't matter, right? In terms of conservation of energy, it doesn't matter, okay? So that's one way to think of it, like conservative. I don't really like that, to think of these types of forces as being that. That's a little bit harder for me to understand. Path dependent versus path independent. The book starts with that definition. I like to think of these forces as forces that have the potential to store energy. Right? That's how I like to interpret these things. If they have a potential to store energy, then they're considered conservative, right? This, right? Back to this example right here. Take my coffee mug. I lift my coffee mug to this height right here. What happens if I let go of this, right? Energy, right? Energy is going to be converted to kinetic energy. It's given me back, right? I lift it, I let go of it, it drops, right? It drops. And so it's stored energy. When I'm holding this, there's stored energy in this thing, right? Everybody agree with that, right? As soon as I let go of this thing, boom, it's accelerating back towards the ground, and it's going to increase velocity. That's stored energy, right? Same thing with the spring. If I compress a spring and I'm holding it compressed, as soon as I let go of that spring, that bitch is shooting back out. right? Or if I pull it out and it's shooting back in, there's energy stored in that system. That's how I like to think of these things. And that's how I think you should interpret these things as well. It's way easier to think of them that way, okay? Forces that can have potential to store energy are considered conservative, right? Which is great because we're gonna call those things, or let's give you an example. We're gonna call it potential energy is what we're gonna do. Examples would be springs and gravity. That's the concept, right? They have potential to store energy, and so we're going to call those things potential energy. Right? In our equations, right? I will say that if you are following along in the book, right, and reading through the book, they start out, and this is confusing as hell, but they start out and they interpret these conservative forces, and they actually treat them as forces, and they talk about how the spring does work over, between two states, and they talk about how mass times gravity does work between two states. Like it treats it as a force, and then later on they go, oh, never mind, treat it as potential energy, and it confuses the shit out of you, because what ends up about a quarter of you start doing both. They put the springs and gravity in doing work, and they put the springs and gravity in potential energy. Don't do it. Just don't ever put it in doing work. Always just include it in as potential energy. That's my recommendation. Don't do what the book does and have it confuse you. Okay? So potential energy, they call it V. Why? Just to confuse the shit out of you, because there's another V in your equations, right? There's a velocity floating around. A lowercase v is a velocity, but for whatever reason, the book calls potential energy as a capital V, okay? As a capital V. When I write my capital V, I'm going to do it just to try to differentiate it. I put a leg on it. Hey. I put a little leg on it just to be like, look, this is not my velocity. I got a leg on it. I only do one leg so that, because my V's sometimes look like U's, and so I gotta just pay attention to the legs. All right, some notes on these guys. Conservative forces can be accounted for in potential energy. It's just a different ways of thinking about the forces, right? It's stored energy. That's the best way to think about it. Right? Something being held up at a certain height, that's stored. As soon as I can release that energy at any time, right? It's the negative of work. Right, it's because it's stored energy. It's the negative work. So you'll see if you go back to like when they're talking about forces doing work and stuff, they end up being negative, and I'll show you that a little bit later. Okay, it's capacity to do work in the conservative field. Just some notes about it. Okay, so what we'll do next time is we'll formally define something that you've done a lot, which is just the work, the potential energy in gravity is just mass times gravity times height, right? You've done that before, and so it's independent of the x and y direction. It just ends up being mass times gravity times height. We'll go through that derivation, and then we'll derive potential energy in a spring, which is just 1/2 ks squared. Right? And then that'll be all the components that we need to then apply this conservation mechanical energy to solve problems, which is money. A pretty straightforward methodology. All right, great. Have a good weekend.